Okay. Have you ever, like, felt an earthquake and wondered just how powerful these things can get? Like, what if it just kept getting stronger? Like the big one, you know?
Oh.
Could it, like, split the earth apart?
Yeah, it's a question that people have been thinking about forever.
Right. So today we're going to deep dive into earthquake magnitudes and see if there's actually a limit to how strong they can get.
And spoiler alert, the Earth itself might actually have some limits.
That's right. We've got some fascinating research here that suggests that there's like some built-in safety features that might prevent a true megaquake.
Yeah, it's pretty amazing when you think about it. All these forces shaping our world, but there are also these kind of limits in place.
So to get started, we got to talk about faults, those breaks in the Earth's crust where all the tectonic energy gets released.
Exactly. And the size of the fault actually plays a huge role in how strong the earthquake is.
Okay, so bigger faults equal bigger earthquakes.
Yeah, pretty much. I mean, the longer and deeper the rupture, the more area that's involved, and so the more energy is released.
Makes sense. But I'm guessing it's not quite that simple.
You got it. There's another piece to this puzzle, and that's segmentation.
Segmentation.
Yeah. So fault lines aren't just like these perfectly continuous cracks. They're broken up into segments by things like seamounts or changes in how thick the sediment is.
So these segments, they're like barriers that prevent a single massive rupture from just going along the whole fault.
Exactly. It's like a built-in safety feature. And this is especially important when we talk about subduction zones, where one tectonic plate goes under another.
Yeah.
Those have the potential for like the biggest ruptures. But even the longest subduction zones are still broken up, preventing a single catastrophic megaquake.
So the Earth has a way of breaking up those massive fault lines. But what about all that pent-up energy? Where does it go if it can't all be released at once?
That's where stress drop comes in. Basically, it's the difference in stress on a fault before and after an earthquake. And usually a higher stress drop means a stronger earthquake, but even the stress drop has limits.
So there's a cap on how much energy can be released, even on a large fault.
Exactly. Because of things like the strength of the rocks themselves, the friction between them, and how the Earth's crust responds to stress, all limit how much stress can be released at once.
It's like if you try to bend a metal rod, you can only bend it so far before it snaps.
Exactly. That's a great analogy. And that brings us to another fascinating factor that limits earthquake magnitude: frictional heating.
Frictional heating. Okay, tell me more. This sounds cool.
So picture this. You have these enormous rocks grinding past each other during an earthquake, right?
Is right.
There's a ton of friction there. So what happens?
I'm guessing it creates a lot of heat.
Exactly. A
Yeah.
tremendous amount of heat. And that happens on the fault plane during a large earthquake.
Okay, so all that friction creates heat. But how does that actually limit the earthquake's magnitude? It seems like it'd make things more intense.
Yeah, you'd think so, right? It's kind of counterintuitive. The heat actually can make things worse at first by making things slip even more, but then it starts to mess with the stability of the fault.
So it's like the fault has a built-in temperature gauge. Like once it gets too hot, it can't slip anymore?
Yeah, think of it like a natural feedback mechanism. The more the fault slips, the more heat is made, and eventually that heat disrupts the fault's ability to slip smoothly. It's like it hits a limit.
That is so cool. So we've got fault segmentation, those stress drop limits, and now frictional heating all working together to prevent those truly apocalyptic earthquakes.
Absolutely. It's like the Earth has this incredible system for keeping things in check.
Hmm.
But before we get too comfortable, we need to look at the evidence, right?
Yeah. Have we actually ever seen earthquakes that push those boundaries?
Well, there are some famous ones, like the 1964 Alaska earthquake. That was a magnitude 9.2. And then there was the 2004 Sumatra Andaman earthquake, which was like between a 9.1 and 9.3. I mean, those were massive.
Yeah, those were devastating earthquakes, but they're still less than that theoretical maximum, right?
Exactly. And even more interesting, when we look back thousands of years using paleoseismic data, we still don't see signs of anything bigger than like a 9.5 or 9.6.
Wow. So even over thousands of years, no sign of a true megaquake. But, okay, what if we just ignored all those limitations for a minute? Could we at least calculate what kind of earthquake would be theoretically possible? Like if the Earth just went crazy?
Well, some scientists have actually crunched those numbers, and they say under some really extreme and unlikely conditions, a magnitude 10.5 earthquake might be possible.
A 10.5. Wow. Okay, so what would it take for that to happen?
So imagine this. A massive fault rupture that's not broken up at all, and it spans thousands of kilometers, right?
Right.
And then that fault slips on average over 40 meters.
Hold on. 40 meters. That's like The height of a 13-story building.
It is. But remember, this is all theoretical. In reality, there are so many things preventing this from happening. The segmentation of faults, the friction between the rocks, the stress drop limits. It just makes an earthquake that massive incredibly improbable.
Okay, that makes me feel a little better. But are there any other clues out there that support this idea of a magnitude limit? We've talked about fault mechanics and historical records, but is there anything else?
There is. And it's a way that we can actually see the Earth regulating itself in real time. And that's geodesy. Techniques like GPS and INSAR, that stands for Interferometric Synthetic Aperture Radar, allow us to track how the Earth's crust is moving.
Wait, we can watch the Earth's crust move? That's amazing.
It is. And what's really neat is what these measurements show us is that the areas with high strain rates, places like those subduction zones we were talking about, have these locked patches. And that's where stress is building up. But here's the thing. These locked patches rarely get bigger than a few hundred kilometers before they release some of that built-up stress, either through smaller earthquakes or what are called slow slip events.
So it's like the Earth has pressure release valves.
Yeah, exactly. And when we look at all this data going back centuries, it becomes clear that these smaller events, along with the segmentation of faults, keep enough strain from building up to create those monster earthquakes.
Okay, so we've got fault mechanics, the historical record, and now these real-time measurements all saying the same thing. The Earth has a way of putting a lid on how big an earthquake can get.
Yeah.
But is there a ANY chance, however small, that we could see an earthquake larger than a 9.5? Could some of those safeguards fail?
Well, it's definitely something to think about, and it kind of takes us into what-if territory again. It's incredibly unlikely, but some researchers have explored the idea of a magnitude 10 earthquake under some very specific and improbable conditions.
Okay, so let's play what if then. What would have to happen for a magnitude 10 earthquake to occur?
Well, imagine a subduction zone that's unusually straight, no major barriers to stop a rupture, and that zone has been locked for thousands of years, letting stress build up to incredible levels. And then that fault slips, like tens of meters in a single event.
Wow, that's a lot of ifs. But even then, we're still just talking about a single earthquake, right? Not the Earth splitting apart or anything.
Exactly. And we have to remember that the data really does suggest that the Earth has a pretty reliable system for regulating these magnitudes. It keeps things well below those truly apocalyptic levels.
Okay, well, that makes me feel a lot better. But I think we need to take a break and process all of this incredible info. When we come back, we'll dive into some of the most fascinating evidence that supports these magnitude limits. Stay with us. Okay, welcome back. Before the break, we were in what-if territory, talking about magnitude 10 earthquakes. It's kind of mind-blowing to think about, but it sounds like they're super unlikely.
Right, it's definitely out there stuff. But you're about to tell me about some of the evidence that supports these magnitude limits, like those dynamic rupture models.
Yes, those are so cool. Tell me more about those.
So they're basically computer simulations that let scientists study how earthquakes happen. They factor in all kinds of stuff, like the physics of how faults break, what different types of rocks are like, even the shape of the Earth's crust.
Wow, so they can actually simulate an earthquake. That must be incredibly complicated.
It is, but that's what makes them so useful.
Yeah.
We can use them to explore all sorts of scenarios, like what happens if a fault tries to rupture beyond those segment boundaries we were talking about.
And what do they find? Do the simulations ever show just one giant rupture that rips through a whole subduction zone?
That's the thing, they don't. Even when you try to create the perfect conditions for a massive earthquake, the ruptures almost always stop at those segment boundaries. Sometimes a big slip can jump from one segment to another, but each jump kind of saps the energy from the rupture, and that puts the brakes on the earthquake's magnitude.
So even in a computer simulation where you can basically control everything, it's almost impossible to make an earthquake go beyond those magnitude 9s. That's amazing. It really shows how effective those natural safeguards are.
It does. But dynamic rupture models are just one piece of the puzzle. Remember, we talked about paleoseismic records. They're another piece of evidence.
Right. The traces of past earthquakes that are left in geological formations.
Yeah.
So what can they tell us about the biggest earthquakes?
Well, it's like being a detective, you know? You dig through layers of sediment and rock looking for clues about past earthquakes. Things like evidence of tsunamis, landslides, even changes in the coastline that can all point to a major earthquake.
So it's like reading the Earth's diary.
Exactly. And when we look at these records, and we're talking thousands of years here, we see a pretty clear pattern. Earthquakes in the magnitude 9 range, but nothing bigger.
Yeah.
Like there's a limit that the Earth just doesn't seem to go beyond.
So no matter how far back we look, no sign of a truly monstrous earthquake.
Yeah.
It's really starting to look like this upper limit is pretty solid.
It is. And remember those geodetic measurements we were talking about, how we can track the Earth's movement in real time? Well, that data supports this idea too.
Right. GPS and INSAR, they measure how the Earth moves, right?
Yeah. And when we analyze that data, we see that even the biggest earthquakes, those in the magnitude 9 range, are often followed by lots of smaller earthquakes, called aftershocks. These aftershocks help to release any extra stress that didn't get released in the main earthquake.
So aftershocks are kind of like the Earth's way of cleaning up after a big earthquake,
Hmm.
making sure the stress doesn't build up again.
Exactly. But here's what's really cool. The size and location of those aftershocks can actually tell us something about how big the main earthquake was.
Wait, really? How does that work?
Okay, so think about it. If a really, really massive earthquake happened, you'd expect to see a ton of huge aftershocks.
Right.
Because if the main earthquake could release that much energy, there should be tons of stress left over to fuel those aftershocks.
That makes sense. Big earthquake, big aftershocks.
Right.
Yeah.
But that's not what we see. Even after the biggest earthquakes, the aftershocks are still relatively small and they're clustered in a certain area. What that tells us is that the main earthquake, even a magnitude 9, couldn't have been that much bigger because there just wasn't enough extra stress to create those monster aftershocks.
Wow. So even the aftershocks are telling us that there's a limit. It really does seem like we've got a solid case here. But I do have one more question. If the theoretical maximum is a magnitude 10 or 10.5, why do a lot of those hazard models, the ones that governments use to plan for earthquakes, focus on magnitudes in the nines?
That's a great question. And it really comes down to the difference between what's theoretically possible and what's actually likely to happen. Sure, a magnitude 10 earthquake could happen, but it's so unlikely it's not something we really need to worry about for most hazard assessments.
So it's about balancing risk and resources.
Exactly. Think about it this way. If you're designing a building in an area with lots of earthquakes, you want to make sure it can handle the biggest earthquake that's realistic. But you don't necessarily need to design it to withstand an earthquake that's so unlikely it might never happen in the lifetime of that building.
Okay, yeah, that makes sense. You wouldn't want to overbuild something for an earthquake that's basically impossible. But are there any places where a magnitude 9 earthquake IS considered the most likely maximum?
There are, like the Cascadia subduction zone, that runs along the coast of the Pacific Northwest. Based on how long it is and the geological records, the biggest realistic earthquake there is estimated to be around a magnitude 9 to 9.3.
Wow, so for them, a magnitude 9 is like the worst case scenario, and even that is incredibly rare.
Exactly, and it highlights something important. While we can talk about a theoretical maximum for the whole planet, the actual biggest earthquake for a specific region depends on the geology and tectonics of that specific area. Some areas might be able to have a 9.5, while others might only be able to have like an 8.5.
So the answer to what's the biggest earthquake possible really depends on where you are.
Exactly. It's all about the local context. But even when we look at the places that could have the biggest earthquakes, the evidence still says there's a limit somewhere in the mid-nines, not those crazy double-digit magnitudes.
Okay, so we've got fault mechanics, computer models, historical records, even real-time measurements, all telling us the same thing. Earth has a way of limiting how big an earthquake can get, keeping things below those apocalyptic levels. But I gotta ask, are there any wild cards? Anything that could throw off this whole system and cause an earthquake bigger than we think is possible?
No, that's a great question, and it takes us into the realm of the totally unexpected. It's tough to say what nature might throw at us, but there are a few things that scientists have considered, even though they're pretty speculative.
Okay, so what are these wild cards? What could mess with this magnitude limit?
One thing, and this is really unlikely, but one thing that's been explored is a big impact from space. Now, we're not talking about a planet-killing asteroid or anything, but even a smaller impact could potentially trigger some serious seismic activity, maybe even on a scale we've never seen before.
So like a cosmic billiard ball hitting Earth and causing a huge earthquake.
It's definitely an interesting idea. But remember, this is all speculation. The energy from an impact wouldn't necessarily all go into a single fault, and the effects would be super complex and tough to predict.
Yeah, it wouldn't be like a regular earthquake that starts from a fault. So what other wild cards are out there?
Another possibility, and again, this is super speculative, is a massive volcanic eruption. We're talking about a super volcanic eruption, something way bigger than anything we've seen in recorded history.
Oh, wow, like the Yellowstone supervolcano erupting? I've heard that could have global consequences.
Exactly. An eruption that big could definitely cause some major ground shaking, and it could trigger earthquakes nearby. But again, the energy from a volcano is different from the energy from a tectonic earthquake. It's not a sudden slip along a fault. It's a much more gradual release of energy as magma rises and erupts.
So even a supervolcanic eruption wouldn't necessarily mean a super high magnitude on the earthquake scale.
Exactly. It would be a totally different kind of event. And while these wildcard events like impacts or supervolcanic eruptions are definitely dramatic and potentially catastrophic, they wouldn't necessarily break the rules of fault mechanics and stress limits that we've been talking about. The Earth's system for regulating earthquake magnitudes is incredibly robust, and it's unlikely that even these crazy events could totally overcome those limitations.
Okay, so it sounds like even those wildcards are unlikely to change the rules of the game. The Earth's system is really effective at keeping things under control. But before we wrap up, I'm curious, can we learn anything from all of this besides just understanding the limits of earthquakes? Is there any way we can use this knowledge to do something practical?
That's a great question, and the answer is absolutely. Understanding what limits earthquake magnitudes is really important for everything from assessing earthquake hazards and mitigating risks to designing buildings and infrastructure.
So this knowledge can actually help us be better prepared for earthquakes.
Absolutely. If we know what the biggest possible earthquake is for a particular area, we can design buildings and infrastructure that can withstand the shaking. We can also develop early warning systems and make better evacuation plans to minimize the impact of an earthquake.
So it's not just about satisfying our scientific curiosity. It's about using what we learn to actually protect people and property.
Exactly. And it goes even beyond those practical things. Understanding the limits of earthquake magnitudes gives us a much deeper appreciation for how complex and resilient our planet really is. The Earth can unleash some incredible forces, but it also has this amazing ability to regulate itself so that those forces don't just go totally out of control.
That's a really great point. It's a good reminder that we're not just living on a planet. We're part of this dynamic system that's always changing, but is also really stable overall.
Exactly. And while those apocalyptic scenarios might make for a good movie, the Earth has a few tricks up its sleeve to keep those truly catastrophic events from happening. It's a real testament to the power and ingenuity of nature.
Okay, I'm feeling a lot less worried about the Earth splitting in two. This whole conversation has been amazing. I'm actually really curious to learn more now. Where can our listeners find more information if they want to do their own deep dive into earthquakes?
Well, we've got links to some awesome articles, research papers, even those dynamic rupture models over in the show notes. So if you're ready to go down the rabbit hole, head over to the show notes and get started.
Perfect. Well, that wraps up another fascinating deep dive. But before we go, I want to leave you with something to think about. We've been talking about earthquakes on Earth, but what about other planets and moons? Could they have even bigger earthquakes? And what would those look like? It's definitely a question worth exploring. Maybe we'll come back to it in a future episode. Until then, stay curious and keep exploring. Okay, so welcome back to the show. Before we went to break, we were talking about those what-if scenarios, those cosmic wild cards that could maybe, just maybe, shake things up a bit, literally.
Yeah, those are always fun to think about, those events that kind of push the boundaries of what we think is possible.
Totally. And one thing I've been thinking about is this. We've been talking about the limits of earthquake magnitudes based on how the Earth's tectonic plates are arranged right now. But what about the future? The continents are always moving, right? So could those limits change as the planet changes?
That is a great question. You're thinking long term now, deep geological time. We have to consider those continents. They're always on the move, but it's slow. Over millions of years, they can crash together and form these massive supercontinents like Pangaea, or they can split apart and create new oceans and subduction zones.
So those changes in the plates could actually create conditions for even bigger earthquakes.
Yeah, it's possible. Think about it. Millions of years in the future, there's a new supercontinent, and it's got this giant subduction zone, thousands of kilometers long. That could potentially lead to earthquakes bigger than anything we've ever seen.
Wow, so the Earth's future layout could totally rewrite the rules of earthquakes. That's wild.
It is pretty mind-blowing. But even then, those basic principles of how faults work would still apply. Even a supersized subduction zone would still have those segment boundaries, the friction, and the stress drop limits that we've been talking about.
So those Earth safeguards would still be there, just on a bigger scale.
Exactly. And remember, these tectonic changes take a really, really long time. We're talking millions, even tens of millions of years. So while it's fun to think about the future of earthquakes, it's not something we need to worry about right now.
Okay, good. That's a relief. But this whole conversation has made me realize how important it is to understand how the Earth's tectonic plates work, not just now, but also in the past. Is there anything else we can learn from those ancient earthquakes? Anything that could help us understand those magnitude limits even better?
For sure. Paleoseismology is a really cool field that's all about studying those ancient earthquakes. By digging into the Earth's history, we can learn so much about how big those earthquakes were, how often they happened, and even what kind of impact they had.
It's like those geological detectives we were talking about earlier, right? Looking for clues about the past.
You got it. And the evidence they find is amazing. Scientists have found layers of sediment that were deposited by massive tsunamis that were triggered by ancient earthquakes. We're talking tsunamis so powerful, they left deposits hundreds of miles inland.
Wow, those must have been some incredible events. But can those tsunami deposits really tell us something about how big the earthquakes were?
They can. By looking at the size and how far those deposits spread, scientists can figure out how big and powerful the tsunami waves were. And from there, they can kind of work backwards and estimate the magnitude of the earthquake that caused it.
So it's like a trail of breadcrumbs leading all the way back to the earthquake itself. That's so cool.
I know, right? And what's even cooler is that these paleoseismic records can go back thousands or even tens of thousands of years. It gives us a peek into what earthquakes were like way before humans were around to write it down.
So we're talking about a time when earthquakes were shaping the planet long before we were even here. It's amazing. But what do those ancient records tell us about how big earthquakes can get? Do they support the idea that there's a limit?
They do. When we look at those records, we see the same pattern that we see today. There's evidence of lots of earthquakes in the magnitude 9 range, but nothing that clearly shows a magnitude 10 or bigger. Seems like the Earth has this natural limit that it just doesn't cross, even over super long periods.
So it's not just a recent thing. This limit seems to have been around forever. It's like the Earth is constantly changing, but there are these basic rules that always apply. And one of those rules seems to be this cap on earthquake magnitudes.
Exactly. And that's a pretty powerful idea. It tells us that even though the Earth can create these massive forces, they're ultimately controlled by the planet's own systems. It really shows how complex and resilient our planet is.
I totally agree. Well, I think this brings us to the end of our deep dive into earthquake magnitudes. We talked about fault mechanics, those cool computer models, the historical record, and even evidence from super old earthquakes. And it all points to the same conclusion. The Earth has this awesome ability to regulate itself, keeping those truly catastrophic earthquakes from happening.
Well said. It's so important to understand these forces of nature so we can prepare for them and be more resilient.
Absolutely. And even though we've been focusing on how big earthquakes can get, it's important to remember that even those magnitude 9 earthquakes, even though they're rare, are still unbelievably powerful. They can cause a lot of damage and really impact people's lives. So even though we know that Earth had these safeguards, we can't forget about studying these events, learning from them, and being as prepared as we can be.
I completely agree. That's the key to living on this dynamic planet.
So that's it for today's episode. Thanks for joining us on this deep dive. We covered a lot, but there's always more to learn. If you want to keep exploring, we've got tons of resources in the show notes. And if you have any questions or thoughts, let us know. You can find us on social media or send us an email. Until next time, stay curious.